So the next sort of level that we need to hit is we need to be able to understand how the entropy changes during a chemical reaction. So delta S, really what we're looking at is delta S of the system. So delta S of the system, or in other words, the delta S for us for a chemical reaction. And the primary thing we look at is states, solid, liquid, or gas. And then if it's gases, we look at the moles of gas that are present. So take a look at the first reaction. This is A. And we say it's C3H8, right? This is gas. O2 is a gas. It forms carbon dioxide and water. These are all gases. So we're looking at all gases. So then what we need to do is look at the moles of gas. And when we look here, right, I have 1, 5, 3, and 4. So if I add those things up, I have 7 moles on the product side, 6 moles on the reactant side. So I have more moles of gas, which means more degrees of freedom. So for the reaction, what that means is delta S for the reaction or the system is going to be a positive value. So what this question is actually asking us is to find the delta S for the system, which we just did, and then we also have to figure out what the sign of delta S of the surroundings is, and then we have to predict whether or not it's going to be always spontaneous at low temperatures, spontaneous at high temperatures, and possibly, I didn't check, it may never be spontaneous for that matter. It might be never spontaneous. I'm not sure that option is in any of these questions, but we'll see. Okay, so what is delta S of the surroundings, right? Well, remember, delta S of the surrounding is based on the energy transferred from the system. So let me do it this way. Delta S of the surroundings is equal to Q of the surroundings divided by T. And then Q of the surroundings, it will be the opposite of the Q of the system. So again, delta H of the reaction is the Q per mole of the reaction. So that means Q of the surroundings will be plus 2,044 kilojoules per mole of reaction, which means delta S of surroundings will be positive. So what does that mean? Right? There's never a situation where it's not spontaneous. Since the enthalpy change is saying it's spontaneous, and the entropy change is saying it's spontaneous, then there are never any temperature conditions at which it'll be non-spontaneous. So A is under all conditions or all temperatures. Okay, so let's take a look at B. Or this one's a little bit trickier. Well, I have this, right? So based on what we just talked about, that means the Q for this, it's endothermic. The Q surroundings will be negative since delta H of the reaction is positive. So for B, not much room on this slide, sorry. I'll make sure I have more room on my later slides. Delta H, this is for B. Delta H of the reaction is positive, so that means delta S of the surroundings is negative. All right. Now, what is delta S of the reaction? And what you'll notice is that I have 2 moles of gas here, and I have 2 moles of gas here. So it's sort of like a balance, right? So is it going to be 0, right? It could possibly be 0 if the degrees of freedom in the molecules was the same. But N2 and O2 have less possible orientations than NO does. So for example, N2 has only one way it can be oriented, right? And then NO could be either this way or this way. And as a result, each mole of gas on the products has more degrees of freedom, translational freedom really, than the moles of gas on the left side. So delta S is positive for this. And the reason is because NO has more entropy. Okay, so what does that mean, right? So if I look at the reaction, I know that delta S of the system is positive. But and this is a constant. This is just dependent on the chemical reaction. This is just dependent on the chemical reaction. So, but what happens for delta S of the surroundings? Delta S of the surroundings, that's going to be the negative delta H over T. Now, if T is really big, and remember, this is a negative value because delta H is positive for this reaction. So that means this is a negative term up here. So this is favoring entropy. This is not favoring entropy. And remember, delta S of the universe is delta S of the cis. Did it again. Plus delta S of the surroundings. So what that means is, as temperature increases, the surroundings entropy effect becomes less important, and the entropy effect of the system is what predominates. So at low temperatures, right, this reaction would be non-spontaneous because delta S of the surroundings will be big. But on the other hand, at very high temperatures, then this factor becomes less important, and you're just left with the delta S of the system. So the result is at low temperatures, it'll be non-spontaneous, but at high temperatures, it will be spontaneous. So I want to lay that out a little more cleanly. I realize, after the fact that I could just probably make another slide. For B, I know delta S of the system is positive, favors entropy, right? And then delta S of the surroundings, that's equal to negative delta H of the reaction divided by T. As temperature increases, this term becomes less important at high temperatures. In other words, the entropy of the system is what's going to matter at that point. So that means at low temperatures, it'll be non-spontaneous, but at high temperatures, it can become spontaneous simply because this term becomes less important. So this is spontaneous at high temperatures. Okay, so let's go ahead and do C. Okay, so in C, we have 3 moles of gas on the left and 2 on the right. So delta S for the reaction is negative. Now, delta H of the reaction is positive, so that means delta S of the surroundings, right, is going to be delta H, negative delta H of the reaction, over T. So since delta H is a positive value, right, that means this term up here is negative. So the entropy of the reaction doesn't favor. spontaneous reaction. And this also doesn't favor spontaneous reaction. And there's no situation, if you think about it, even if I go to absolute zero, right, or if I go really, really large, in which this term won't be negative. And so as a result, entropy for the universe is always negative, and this reaction is never spontaneous. So this one doesn't favor either, I should say. Okay, now let me show you another way that people analyze these reactions. And they do that by looking at delta G. And delta G is equal to delta H minus T delta S. And they just look at delta H and they say, oh, well, delta H is positive or negative. So let's do it for B. And so for B, delta H was positive. But delta S was positive as well, right? So in other words, for a reaction to be spontaneous, then delta G has to be negative. So at low temperatures, let's say you were at zero, just hypothetical 0 Kelvin, right? This term would go away and delta G would be positive and non-spontaneous. But since delta S is a positive value, as you keep multiplying it by a larger and larger temperature, you're subtracting away in the free energy. So as you subtract away, eventually at some temperature, this reaction will become spontaneous, simply because this part becomes greater than this part. Okay, so when you're trying to explain it in terms of entropy, all you have to do is look at this term, and then you look at this term. This term is telling you what it will be at low temperature. This term will tell you what it'll be at high temperature. At high temperature, the influence of delta H becomes less important, and at low temperature, it becomes more important. We can do the same thing with C, right? Delta H is positive. And then delta S is, I already forgot what we said, negative. Delta S is negative, yeah, sorry. I just looked at it and forgot it already. Oh yeah, it's right here. Delta S is negative, and the result is, right, there is never a situation where you have a temperature that's, real, that this whole thing isn't positive, because this is minus T delta S. If this is a negative term, then you're really just adding this term on. And so this reaction would never be spontaneous, unless, of course, you maybe could go to negative Kelvin, which we can't do.